Hello everyone and welcome to our presentation. What we like to present to you today is RC bandpass filter, and this is my group member's name. So, what is bandpass filter? We can say that a bandpass filter is a combination of both low-pass filter and high-pass filter. A type of passive RC filter that passes a selected range or band frequencies. The name of the filter itself indicates that it allows only a certain band of frequency and blocks all the remaining frequency. By connecting or cascading together a single low-pass filter circuit with high-pass filter circuit, we obtain a bandpass filter. In audio applications, sometimes it is necessary to pass only a certain range of frequency. This frequency range does not start at 0 Hz or doesn't end at very high frequency, but these frequencies are within a certain range, either wide or narrow. Bandpass filter passes signal within a certain band or spread of frequencies without distorting the input signal or introducing extra noise. This band frequency can be any width and is commonly known as the filter bandwidth. The cut-off frequency of the low-pass filter must be higher than the cut-off frequency for the high-pass filter.
Next, I'm going to explain about RC bandpass filter circuit. From the top at the left side of this slide, you can see the high-pass filter, where high frequency will flow right through the capacitor, but the capacitor will block the low frequency. Meanwhile, on the right side is the low-pass filter, where we need to switch the resistor and the capacitor, so we have the circuit like this. The high-frequency signal will flow through the capacitor, going back to ground, so it will be filtered out by the capacitor. So, the low-frequency signal will flow to the output. Therefore, by combining high-pass filter and low-pass filter, we will get a bandpass filter. In the frequency response graph of the bandpass filter, you can see that F1 is the cutoff frequency for high-pass filter since it correlates to C1 and R1. F2 is the cutoff frequency for low-pass filter, which correspond to C2 and R2. And the gain decreases by 3 dB between the maximum level and the cut-off frequency. Meanwhile, FR stands for center frequency. Since FR is the geometric mean between F1 and F2, its formula will be FR is equal to square root F1 times F2. B stands for bandwidth, which is the difference between F2 and F1. And to obtain F1, we will use the formula F1 is equal to 1 over 2 pi R1 C1. Same goes for F2. We will use the formula F2 is equal to 1 over 2 pi R2 C2. So now let's talk about how this bandpass filter circuit works. Firstly, low frequencies are blocked by C1. Capacitors block low frequency signals but still allow high frequency signals to pass through. And then the high frequencies and mid-level signals will pass through C1. Mid-level signals are usually labeled as FM. And then the high frequency signals will be sent to ground by C2 as the capacitive reactance will be low. And this allows the mid-level frequencies to go to the output. So, we can conclude that bandpass filter blocks the low frequency signals and the high frequency signals in order to allow the mid-level signals to make it through the output.
The next part is about the types of bandpass filter. There are two types of bandpass filter, which are wide bandpass filter and narrow bandpass filter. For wide bandpass filter, it can be formed by cascading the two sections, which is high pass and low pass. For the formation of plus minus 20 dB per decade bandpass filter, two sections, first order high pass section and first order low pass section, are cascaded. Same way for the formation of plus minus 40 dB per decade bandpass filter, the second order high pass section and second order low pass section is connected. So the order of low pass and high pass will govern the order of the bandpass filter. For the second types of bandpass filter, which is narrow bandpass filter, only one OP AMP is employed in this filter. This filter has some unique features which are very useful. It is called a multiple feedback filter due to two feedback paths. OP-AMP here existed is used in inverting mode. The designing of a narrow bandpass filter is done for specific values of FC or Q and BW. Next is about the application of bandpass filter. These filters are widely used in wireless transmitter and receiver. Next, these band pass filter are also used in instruments and application of medical and seismology. One of the best application of band pass filter is audio amplifier circuits. We can observe simply as the speaker will play the desired range of frequencies and will attenuate the remaining. Thirdly, in audio signal processing, this bandpass filter play a vital role by allowing the particular frequencies and removing the unwanted. Next, the bandpass filter is effectively used in optimizing signal to noise ratio, S/N ratio, and even the sensitivity of the receiver. Bandpass filter also most common uses in implementation of discrete Fourier transform to separate out harmonics. Other than that, it is also used in optics like lidars, laser, and many more. Lastly, as these bandpass filters are specially designed to allow a particular band of frequencies, so it is widely used in communication system.
My name is Nur Fatiha binti Amin, and now I will be explaining the example of RC bandpass filter. For high-pass filter stage, the value of the capacitor C1 required to give a cut-off frequency FL of 1 kHz with a resistor value of 10 kΩ is calculated as, we can see the formula here, which is C1 is equal to 1 over 2 pi FL times R. From all of the information given, we can find C1, which is 1 over 2 pi times 1000 times 10,000, and it is equal to 15.9 nanofarad. Next is the low-pass filter stage. The value of the capacitor C2 required to give a cut-off frequency FH with a resistor value of 10 kΩ is calculated. We can get C2 from the formula 1 over 2 pi times FH times R. Okay, we can substitute all of the information like C2. Okay, 1 over 2 pi times 30,000 times 10,000. Okay, we can get the answer 530 PF. Then the values of R2 and C2 required for the low-pass stage is to give a cut-off frequency of 30 kHz are R equal to 10 kΩ and C equal to 530 PF. However, the nearest preferred value of the calculated capacitor value of 530 PF is 560 PF, with the values of both of the resistance R1 and R2 given as 10 kΩ and the two values of capacitors C1 and C2 found for the high pass and low pass filters as 15 NF and 560 PF. Example 2. Using of 10K resistors, design a RC band pass filter with a resonant frequency of 6 kHz and a bandwidth of 9 kHz. From the information, the bandwidth is larger than the resonant frequency. The resonant frequency is square root of F1 times F2, and the bandwidth is F2 minus F1. We have two equations and two variables, which means we can solve this. So let's replace the BW by 9. So 9 plus F1 is equal to F2. So what we can do is we can solve this by substitution. Substitute F2 into equation 1. So we have 6 equal to square root of F1 times 9 plus F1. Square root both sides, so we're gonna have 36 equal to 9F1 plus F1 squared. Arrange it and equal it to 0. We can solve this equation and we get F1 equal to negative 12 and F1 equal to 3. The frequency cannot be negative, so F1 is positive 3 kHz. Now we have F1, so we can calculate F2, and we get F2 equal to 12 kHz. We can see the significant difference between F average and resonant frequency. It is because the bandwidth is more large than resonant frequency. In step 3, let's try to do a circuit. R1 and R2 is 10K resistors, so C1 1 over 2 pi F1 times R1. Substitute from all of the information we get C1 equal to 5.3 nanofarad. Same with C2, we just need to substitute in the info, so we get C2 is equal to 1.33 nanofarad. In conclusion, we can say that a band-pass filter is a combination of both low-pass filter and high-pass filter. The name of the filter itself indicates and it allows only certain band of frequencies and blocks all the remaining frequencies.